Hello, I am Dr. Rashid Ahmed from the Department of Physics of Kohat University of Science and Technology. In the subject of particle physics with the course code PHY 452, we are at the lecture number 5 and the topic is antiparticles and neutrinos. In our previous lectures, we have discussed about the fundamental particles in the particle physics. Today we are going to look at the antiparticles and the neutrinos. So in 20th century, in the beginning of 20th century, two major theories and paradigms emerged in physics, and they become the pillars of physics. The first one is quantum mechanics and the second one is special theory of relativity. So these two theories became the pillars of physics, where quantum mechanics was used to describe the mechanics of very small particles or of a very small size, and on the other hand special theory of relativity presented by Einstein in 1905 is used to describe the mechanics or dynamics of a very fast moving particles. So these two theories actually apply in different regimes. One is to the very small particles and other is to the very fast particles. And the question arises that what happens when we have particles which are very small and also moving very fast. That means we have to apply a theory which is a combination of them. So this is the first point. The second point is that special theory of relativity is a very fundamental theory which actually requires every other theory of physics or nature to obey it. So any theory which does not obey special theory of relativity is not accepted in quantum mechanics, at least in a complete sense. So therefore in 1930s or after 1930s, in 1940s I would rather say, people started to think of a quantum mechanics which is relativistic. Because in a moment I will show you the quantum mechanics in its original form is actually non-relativistic, which means that quantum mechanics does not obey special theory of relativity. So what people actually started to do is to combine these two theories, that is quantum mechanics and relativity, to obtain relativistic quantum mechanics. In doing so, and that is deriving the relativistic quantum mechanics to describe the motion of a very fast particle which is also very small, for example electrons, there were new problems emerged, and interesting and new problems and new insights and new discoveries actually emerged out of this effort to combine quantum mechanics with relativity. So let's see what were these new outcomes and discoveries and what were these new problems. So first of all, I will explain to you now that quantum mechanics is non-relativistic. How could we see this, that quantum mechanics is a non-relativistic theory? So we know that the Schrodinger equation or the time-dependent Schrodinger equation is a postulate of quantum mechanics or is a foundation of a quantum mechanics. But unfortunately the Schrodinger equation is not symmetric in space and time derivatives, and hence it's not relativistic. So what I actually want to say is that this is the time dependent Schrodinger equation. On the left hand side you see this is a wave function which represents a particle, and it's a function of position, that is r and time, and it is I h bar del by del, t is energy derivative. or time derivative, or a derivative with respect to time. On the other hand, on the right hand side, you see an Hamiltonian H and acting on the same wave function. Now if you write this on the left hand side, you see that it is the first order derivative, but if you write explicitly H, this is equal to p square by 2m, where p which is second order derivative, and if you write p or the momentum operator, it is equal to minus I h bar del by del x plus del by del y or del by del z, or if it is in 3 dimensions, so it should be del by del y, and this should be del by del z. So we see that in quantum mechanics, this momentum operator is actually a quadratic or second order derivative. Now relativity demands that the derivatives with respect to space and with respect to time should be symmetric or should be treated equally. The time coordinate and the space coordinate should be treated on equal footing, and they should not be discriminated. So you see that manifestly Schrödinger equation is not a relativistic equation, because it treats the time derivative as a first order derivative and space derivative as a second order derivative. That means this equation is manifestly or obviously a non-relativistic equation. So that was the problem, that the equation is the basics of the quantum mechanics, or the fundamental equation of the quantum mechanics, that is Schrödinger equation, is a non-relativistic equation. So the thing was that to make it relativistic, or to make it obey the special theory of relativity. Now from here you can guess that we can do it in 2 ways. The first way is either to take the square root of this h and make it linear, or take the square of the time derivative and make it quadratic. Actually both approaches were tried, and they resulted into same thing. So let us first discuss the approach that is taking the square of the time derivative and making this equation a relativistic equation. This was done by actually Klein and Gordon, and what they did is they started with the relativistic energy momentum equation, that is E square is equal to c square p square plus m square c4, and tried to derive the Schrödinger type equation from this energy momentum relationship, and they made the following substitutions. That is, for energy they put E I h bar del by del t, and for the momentum they replaced it with an operator I minus I h bar del by del x. So when you put these into here, for example energy operator here and momentum operator here, to make this equation into operator equation, what happens that and also multiply it with the psi, that is wave function, from the right hand side, what happens that we get a new equation which was for the first time derived by Klein and Gordon. And this equation, if you look at it, that it has a time derivative with respect to time, a square over here, and derivative with respect to space del as also a square over here. So it is manifestly a relativistic equation, and it obeys a special theory of relativity. This equation was actually derived by Schrödinger before even deriving his own equation, that is the equation which bears his name, that is Schrödinger equation, but he actually did not publish it for a very interesting reason, which actually later on became a discovery. And that reason was that if you look at this equation, it has a second derivative with respect to time. Now what does this mean? I explain to you this in a moment, but let's look at the Klein-Gordon equation and see what are its problem first. So Klein-Gordon equation, what it gets is over here, that it is the it got the square of the time derivative. So therefore, if you solve it, you will get two solutions for energy. That is, E is equal to plus, because whenever you take a square root, you get a plus sign and you get a minus sign. Now this was exactly the reason that Schrödinger did not publish this Klein-Gordon equation and rather put it away. Later on, when he died, it came out of his drawer. But at that time, Klein and Gordon had already published this equation, so therefore it got their name. Schrödinger thought that what is the meaning of this negative energy solutions. So therefore he rejected his own derived equation and did not publish it. But later on, when Klein-Gordon made the Schrödinger equation relativistic and derived these two energy possible solutions, then they opened a new dilemma where it was necessary to explain the negative energy solutions. We will see in a moment that what solutions came about from this merging quantum mechanics with relativity and what they actually mean. So as I mentioned that we would like to also think about the properties of Klein-Gordon equation. First of all, this equation is for spinless spinless particles such as pi mesons. And secondly, they do not describe particles of having some spin. For example, electron, which has a spin 1 by 2. So therefore, Klein-Gordon equation cannot explain or does not explain the spin particles. So therefore, it is their main drawback that they are only for the spinless particles. And the second is that although the Klein-Gordon equation is actually a relativistic equation, but it's not really a quantum mechanical equation, because this equation does not conserve probability. And this you can check for yourself if you calculate the probability from the Klein-Gordon equation. It will turn out that this does not conserve probability. So therefore, it strictly speaking is not is a quantum mechanical equation. So in order to address these problems, that is, it is for spinless and it does not conserve probability, another scientist called Dirac actually wanted to actually went on the other route of taking the square root of space derivatives and making the equation linear, and he derived another equation actually that got his name, that is we call Dirac equation. So he introduced, in order to derive his equation, that is Dirac equation, he introduced another Hamiltonian called a Dirac Hamiltonian, or Hamiltonian which is linear in momentum and space and time derivatives. So here you can see this is alpha dot with the p and bmc square, and it's all hidden in these alpha, and this turn out to be some matrices, and these matrices actually contain both space and time which are linear. So we see that alpha beta are dimensionless parameters to be determined, and we will see that these are actually matrices. They will turn out to be matrices called gamma matrices or Dirac gamma matrices, and they actually encode all the structure of space and time there, these alpha and beta matrices. But without going into a lot of details, we see that if we substitute the Dirac equation in Schrödinger equation, what we get actually this Hamiltonian into this Dirac Hamiltonian into Schrödinger equation, if we substitute this, what we get is this type of equation. And if we make substitutions for E is equal to I h bar del y del t and P is equal to minus I h bar del y del x, that is making the observables, replacing the observables with their corresponding derivatives, that is energy with a derivative with respect to time and momentum derivative with respect to x. It is energy operator and a momentum operator. So what happens that we end up with this equation, something which is called a Dirac equation. And you see it's quite remarkable that it has the time derivative, the first order, and it also has a space derivative, which is also a first order. So this equation is now first order, it's not quadratic, and it's a first order linear differential equation, and it is a relativistic, manifestly relativistic equation, because it contains the time derivative, first power of the time derivative, and the first order of the space derivative. But if you look at these matrices, these alpha and beta matrices, these are actually gamma matrices, and they are 4 dimensional, they are 4 cross 4 matrices. So therefore we will get 4 solutions of psi, 4 components of this wave function psi. So again we are having 4 particles actually, and what we get that these 4 particles describe 2 of them describe spin half particles, 1/2 and -1/2, and 2 are describing the negative energy particles. So again we are struck in the same problems which we had from the Klein-Gordon. So this equation again does not really remove the problem of negative energy solutions, although it removes other problems of Klein-Gordon equation. For example, it is now this equation can now be applied for the spin particles, that is spin half or half integer particles, and also it conserves probability. So it really is a quantum mechanical relativistic equation, but the same problems still persist with the negative energy solutions. And at the moment then I will go back and tell you that what was the solution to these negative energy. Actually at the beginning Dirac himself proposed that probably it's a C of the negative energy solutions where the electrons are present, and we take out when electrons out of them, then the hole they leave behind them is actually in a negative energy solutions. And at that time he said that these holes are actually protons. So these negative energy solutions are protons. But there were 2 problems with the Dirac C interpretation. The first problem was that we don't see this C anywhere, and the second problem was that the mass of the proton is not really equal to the mass of electron. Therefore proton is not really an electron. But what saved Dirac equation, it was the discovery of positron or antiparticle of the electron in 1932. And after that discovery, people said, okay, these negative energy solutions which are coming into the Dirac equation or Klein-Gordon equation are actually antiparticles of electrons called positron. So they are just the same electrons, but with a positive charge, that is opposite charge of electron. And by this way we discover the antiparticles. And now we know that every particle has its antiparticle. Okay, so far so good. We talked about the antiparticles in the first half of this lecture. Now we go towards the second half of the lecture and we see what are neutrinos actually. For this reason we will go to the beta decay. Now what is beta decay? Actually beta decay is a decay of some particle A into a particle B with the emission of electrons. This happens inside the nucleus when a neutron goes into a proton with emission of electron, and this also happens in the nature. For example, a hydrogen atom can go into the helium atom, or since a neutron is decaying into a proton, so you see the increase of the charge over here. The mass remains the same because electron neutron is going into the proton, so mass almost the same, but just the increase in the charge number. And also you see that this copper goes into zinc, and there we see that the same beta decay happens. Now so far is so good, but the problem is that when a particle changes into another particle, then some of the energy is missing. Here some energy is missing, and this you can see in this graph that the endpoint energies here are varying, they are not constant. On the other hand, we should have this constant energy for the electrons coming out. So what I want to say that whenever for example here when neutron goes into proton plus electron, then this electron, when we get when we repeat the experiment, or we look at the other instance of this, then electrons come out of varying energy. That's the problem. And why it's a problem that we have a varying energy? The problem is that this formula over here tells us that the energy of the electron coming out must be a constant, because this is the formula for the energy of the electron coming out into the beta decay, and this says that it must be a constant. But what we see from the graph over here that the energy is not constant, but it changes and it varies. So in instances when energy is less, where goes the rest of the energy? That was the problem. And this problem was so severe that at the time people like Bohr even postulated that probably the energy is not conserved and missing energy actually is destroyed. But Pauli at that time, a famous physicist, was such a strong believer of the law of conservation of energy that he stated that it is not actually possible that energy is not conserved, but rather this extra energy is taken by another particle known as neutrino. Here you see the bar over it, it is actually anti-neutrino. Basically it's anti-neutrino. Now we know that every particle has its anti-particle, so in order to conserve the charges and spins, everything over in this equation, actually this is the anti-neutrino which is emitting. So basically he was postulating that there is this extra, and its mass is almost negligible, and it is chargeless, so therefore it does not interact with any known way. So therefore neutrino was we were not able to discover the neutrino. But later on many people in 1950s have discovered that neutrinos actually exist, and the neutrinos were discovered, and these Pauli, and we knew that this missing energy is taken by the neutrinos. So we got a new particle now on our hands. This is called neutrino, and its counterpart anti-neutrino. So this way today we have talked about the neutrinos and anti-neutrinos, and now we come at the end our famous way of looking at the counting the number of particles. And you see that now how many particles we have. So we have now basic fundamental particle electron, we have a positron, then we have a proton, and then we have an anti-proton. So there is no name for the anti-proton, a special name like a name for the here for positron, but we have a name for proton and anti-proton, and then we have a neutron, and then anti-neutron, we have a photon and anti-photon, we have a pion and anti-pion. Remember that we discovered this particle, and we have a new muon and anti-muon, and especially a new particle here is now neutrino and anti-neutrino. So if you count these particles at that moment, so we are having now actually 14 particles. It's all about it's almost, you can say, around 1950s we had these number of particles increased to the 14. So now we have anti-particles also included in the list. So these are the references, you might want to look at them. And again to summarize the today's lecture, what we have done is that we have considered the anti-particles and neutrinos. In the first half of the lecture I explained to you that why we believe or why we have anti-particles. Initially it originated from the combination of quantum mechanics, which is actually postulated by Schrodinger equation, and we see that Schrodinger equation is a quantum mechanical thing, and we wanted it to become a relativistic one because we wanted quantum mechanics to obey the special theory of relativity. But what happened that we combined or mixed the special theory of relativity with the quantum mechanics. We got Klein equation, which was then saying that we should have negative energy solutions. And then Dirac came from the other way and derived his equation, Dirac equation, but still the requirement that we should have a negative energy solution were there. And later on we discovered that these negative energy solutions are actually antiparticles of electron, and we got the positron, name to it positron because it has a positive charge. But later on we discovered that every particle has its own antiparticle. Then in the second half of the lecture we talked about the neutrinos, and this is idea related to beta decay. And we know that whenever inside the nucleus a neutron decays into a proton and electron, it emits another particle, it has another particle because of the law of conservation of energy, and that name was given to it neutrino by Pauli. And neutrino is a massless, almost massless, is not really a zero mass particle, and a chargeless particle. And this particle is involved in beta decay. Nowadays it's a huge physics which we say that neutrino physics. It's a huge branch of the physics, and a lot of research is going into the neutrino physics. But anyway, so our total number of particles were now 14, because we had 7 fundamental particles at that time, and 7 to their antiparticles. So around 1950s, this was actually the number of particles we really had. With this, I thank you all.